today I'm addressing some new results that are a collection of different aspects of consensus-based optimization on the sphere. And it is a joint work with several colleagues, in particular with Lorenzo Pareschi from the University of Ferrara in Italy, and also with Philip Sunen, who is a PhD student of mine, and Hui Huang, who was a postdoc with me in the past years. And so this talk it's about optimization, and optimization is somehow at the core of modern machine learning. And so I would explain a little bit why we are kind of interested to this kind of non-convex high-dimensional optimizations. And however, the approach that we follow is pretty new with respect to the practice in machine learning. So let me explain a little bit what machine learning is about. Machine learning is about parametric nonlinear algorithms. So in other words, they are nonlinear functions that are highly parametric. And the parameters are typically fit to data and optimized towards several tasks. Among some of them, feature selections from the data, dimensionality reduction of the data, clustering, classification, regression, or even generation of new type of data that fits the statistics of the data that are already seen. So the nonlinearity and the non-convexity of the data misfit in these optimizations is typically leading to a training phase that is about a non-convex optimization. So the objective function to be optimized is non-convex. Moreover, the parameters that are usually used to construct these parametric algorithms, they are many. Typically, they are over-parametrized algorithms with respect to the training set. So if the training set a certain number of training data, typically the number of parameters exceed this number. And so it makes the optimization non-convex and high-dimensional, and for this reason, in general, a quite hard problem. Due to the high dimensionality, first-order methods, such as gradient descent methods, are used very much in practice because of speed and scalability of the algorithms, but also because they are generically able to escape the trap of critical points. In other words, if you generate at random the initial conditions of this algorithm, the probability that you get stuck on a certain kind of critical point like saddle points is basically very small, or virtually zero. However, these methods, they are even able to compute global minimizers for certain type of machine learning problem where the landscape is nearly convex. But in general, these methods, first of all, they require the function to be differentiable, to be really able to use them. And the second thing is that in certain, for certain kind of task, like training of feed-forward neural networks, there is some phenomena like the vanishing or the explosion of these gradients during the optimization phase that makes the optimization failing. And in general, there is no guarantee that these kind of methods do perform global optimization, which is actually one of the interesting situations in several machine learning problems. However, long before all this hype of machine learning and high-dimensional non-convex optimization in this area, there have been many different algorithms that have been somehow considered in order to realize optimal design of any sort of processes, even the design of a boat or design of certain kind of profiles of machines. It was all optimized by using certain kind of algorithms that fall into the class of the so-called meta-heuristics. Meta-heuristics are used in practice very much more than the typically studied methods in the academic environment. And they are basically designed to orchestrate interactions between local improvements and global understanding of the optimization landscape, and combine typically deterministic and random decisions. So they are very sophisticated type of methods that inject local and global information, random and deterministic mechanisms. Of this algorithm, there is by now a zoo of different methods, starting in the 1960s with the simplest heuristics, but then there's been concepts like the evolutionary programming and several other methods like simulated annealing, very much used in the real-life applications of genetic algorithms and so on, getting to the particle swarm optimization that is one of the most popular and recently proposed. So despite the tremendous empirical success of these methods that really perform very hard optimization with statistical evidence of success, it's really hard to prove it mathematically. And one of the reasons is because of the randomness that is involved, often somehow related to memory mechanism. And so what would happen is that you generate along the iterations complicated dependencies that are very difficult to somehow disentangle and to analyze. Recently, there has been a proposal for a sort of meta-heuristic algorithm that is very much inspired by these meta-heuristics, called consensus-based optimization. And this came with a paper of Pinot and others that I will mention at the end of the talk with a proper citation. And that has been picked from Jose Antonio Carrillo and others and analyzed by them. And also I will refer at the end of the talk to a proper citation. And consensus-based optimization is focusing on instantaneous stochastic and deterministic decisions, which means that the dependencies and the way you can analyze this method become a more somehow a simple process to understand. And in order to establish a consensus among optimizing agents that we may call even particles inspired by physics on the location of the global minimizer. At the moment, this is a sort of high-level description, and I will get to formulas in a moment, but the idea is that the particles are moving both deterministically and randomly, exploring the space and try to, in a certain sense, find a consensus on the possible position of the global minimizer. Due to the instantaneous decision mechanism that is also stochastic, the evolution has the virtue that can be interpreted as a system of stochastic differential equations. So the algorithm itself, that is an iterative process, a discrete time, can be interpreted as a discrete time approximation of a stochastic differential equation system. And the stochastic differential equation system for a large particle limit, or for the number of agents going to infinity, let's say, may be approximated by the solution of a deterministic partial differential equation of mean field type, a Fokker-Planck type of equation. The large time behavior of the solution of the PDE is analyzed then by classical calculus. And one can prove that somehow the solution tend to concentrate to a delta on a point that is not too far from the global minimizer. So this is the way one can approach the analysis of these methods by the three-level approximation. The first level approximation is the discrete time approximation of the SDE. The SDE can be approximated by the PDE, and the large time behavior of the PDE is then analyzed. There's one problem, though, that somehow in the original formulation of this kind of optimization on the flat, so on the Euclidean space, there is not enough compactness in the system that would allow, in general, to be really able to prove rigorously the mean field limit, which means that the approximability of the SD system or the description of the SD system for the large particle limit by the law or the somehow the solution of the corresponding Fokker-Planck equation. This is the case for unbounded objective function. For bounded objective function, one can use, in a certain sense, this property to be able really to derive this mean field limit. But in general, this is a sort of open gap in the approach. And so in the original papers, Carillo and others, they actually studied the large time behavior of the mean field limit equation and as a sort of meta description of what is going on. So inspired by this theoretical gap that is due to somehow some lack of compactness, and the fact that problems bounded on compact sets are still very, very interesting for many, many applications, and as I'm going to describe for the moment, motivated us to try to close this theoretical gap and bring this kind of theory to optimizations constrained on compact sets. In order to avoid boundary conditions, we have been considering the problem of consensus-based optimizations over compact manifolds without boundary. And I will get to that in a moment. But let me show you how these methods work on the flat and how they behave and why they are so intriguing and surprising to a certain level. So here we have an objective function that has a zillions of local minimizers, and no gradient method would be able to really find this global minimizer, and unless just by chance, by randomly picking the initial condition, you would be very close to it, right? And here, instead, starting from far away, a very large group of particles would allow you, nevertheless, in a reasonable time, to detect where the global minimizer is, and eventually all the particles would agree on that, and they would converge to this global minimizer. So this is a really remarkable fact, impressive. The question is how scalable can be. So can we scale it to very high dimensional problems and make it work in there and have some proof of convergence? This is the fundamental question that we would like to address. Okay, so as I said, the easiest and nicest possible prototype for a consensus-based optimization of a compact manifold is certainly starting with the problem of optimizing a non-convex function over the sphere. Okay, so how can we do that? So what would be a good prototype for a consensus-based optimization method for the sphere? As I said, the algorithms, they are necessarily interpreted as a discrete time approximations of SDE systems. So, which means that it would be better to start from the SD system and then discretize it with your favorite algorithm. Okay, so the system is about n interacting optimizing agents or particles that somehow are governed by a certain kind of stochastic dynamics expressed here in Ito form. And the dynamics looks quite complicated, and I'm going to describe it to you in a moment. And so here we do have a couple of things to be introduced. First of all, we need to introduce the empirical probability distribution of the particles. That is this train of delta Diracs that is described by rho n. So rho n, it's a measure that is counting the particles. With this, we are computing a certain center of mass of the particles. And this center of mass is called V alpha, and it is computed as a weighted center of mass of the particles, where the weight given to a certain particle is inverse proportional to an exponential of the objective function that you want to minimize. In other words, those particles that have a lower level of the objective function is more important, and those that have a very, very high level of this energy, they become extremely thin particles, not very important particles. And everything is regulated by a parameter alpha that is also deciding or intervening in the in this weighting of the particles. So this point, it's a convex combination of the particles. So it's really a sort of weighted body center. And since the particles are on the sphere, this point does not lie on the sphere. This point actually lies inside the sphere. Okay, this point is a sort of, if you want, is a proxy for a global minimizer. Unfortunately, it's a proxy that lies inside the sphere. So what do? Well, we project this point onto the tangent space of each particle by using the projector P. Here there is a projector P that depends on the position of the particle in position V. And we project in the first term this point on the tangent space, and we create a tangent vector that determines the velocity, the direction where that particle wants to move. And it moves in the direction, in a certain sense, of this consensus point, but actually in the sense of the tangent projection. This is the deterministic drift. The particles are shifting in the velocity in that way, and somehow this is a drift that is fully deterministic. The second term, so that appears in this stochastic differential equation, it's the projection of the embedding Brownian motion. So it's a Brownian motion in RD, that is the embedding space, that is projected onto the tangent space. And somehow its strength depends on whether this particle is already very close to the consensus point. So if the particle is very close to the consensus point, in other words, the consensus point needs to be already very close to the sphere, then this particle would move very randomly, but not too wildly. But if the particle is very far from the consensus point, means that this particle does not yet agree with the others about this consensus point, and so this particle will continue to move quite wildly, exploring around. for a motion on the sphere, you want to expect the velocity field to stay on the tangent plane, okay, on the tangent space. But this won't be enough for keeping the dynamics on the sphere, because the Brownian motion is essentially an unbounded object. It's an object that in principle is unbounded. And in order to really be able to keep everything on the sphere, and I will explain why this third term comes into the game, you need to have a correction term that comes from Ito calculus. Okay, so this is a sort of second order information that you have to inject in the system in order to keep the system on the sphere. Okay, so this is the system of stochastic differential equations that are defining this consensus-based method. And the way we realize it in practice is by discretizing in time this equation, right? So, and the simplest way to do it is by using a Euler method that in the field of stochastic differential equation means it is called Euler-Maruyama method. And so we are doing a sort of classical Euler step. And in order really to facilitate, to guarantee that we stay on the sphere, we are basically reprojecting the dynamics onto the sphere by renormalization. Okay, so this kind of method is a method of order 1/2, and it is somehow one can show that the introduction of this projection method does not, this projection renormalization does not change the order, and it is a classical, somehow classical method of approximation for this stochastic differential equation. So this is the actual optimization algorithm that you would implement on the computer. Okay, so maybe I'll stop at this point, and I will ask whether there are questions that maybe somebody may want to ask, because somehow the system may be a little bit complicated, but I may like to ask whether it's all clear. Okay, if this is not the case, then I can continue. This is a numerical example of how this method works. You can see here a function that exhibits a certain number of local minimizers that is called the Ackley function. And somehow we consider this Ackley function restricted on the sphere, and we position, sorry, something happens here. And we positioned the global minimizer at the very north pole of this sphere without loss of generality. And what you can see is that the particles are ignoring completely the local minimizers, and they are able to find the global minimizer without too much difficulty. But this is a function where some of the global minimizer is particularly pronounced with respect to the others. But if you use functions that may have multiple local minimizers that are very, very close to the global minimizer, nevertheless, somehow the method is able to find the global minimizer without too much difficulty, at least in moderate dimension. As I mentioned, this is a prototype, the typical prototype problem, the one on the sphere, but we can generalize, or we generalized already, this kind of problems on compact hypersurfaces like the torus. And so we can see here the optimization of the Ackley function over this torus, and again, it appears very clearly that the topology won't be a problem for the method to converge to the global minimizer. Okay, now two things are open, right? So can we prove mathematically that this method does what it appears from the numerical experiments, right? So can we prove the convergence? And so here we have the main theoretical result, and then I will explain the steps that are needed to prove it, and then I will explain step by step how really these steps are mathematically realized. So the assumption is that the objective function is a C2 function. This is an artifact of the proving method. The reason is that the method is a zero-order method, so it does not use any gradient information of the function itself. And we use this regularity exclusively because we are using calculus in order to prove the convergence of this method. And it is due to the proving technique that we are following. We have a recent result that we uploaded a couple of days ago on arXiv of optimization methods on the plane, where we prove that we don't need any regularity of the function E, and we have a way more general approach that would allow somehow to have non-smooth optimization taken into consideration. Instead, it is absolutely fundamental to have a local coercivity property, or what we call also inverse continuity property, that tells you that whenever you have a very low level of the objective function, then you are also very close to a global minimizer. Okay, so this is inverse continuity property is quite crucial for the method to be really able to converge to a global minimizer. These are two assumptions, and under these two assumptions, one can prove the following statement: that for all epsilon, we can assume that the initial datum and the parameters are well prepared, and I will comment about this well preparation of the initial condition and of the parameters later. So for the moment, accept that a little bit of tuning of the parameters and the initial condition has to be done. And we need to have the famous parameter alpha that intervene in the computation of the weighted barycenter large enough. Then the expected behavior of the average particle, and here for the average particle I mean the particle generated by the algorithm, not the SDE system, is really what the algorithm spit out of these iterations. If we average the average particle is expected to be very close to the global minimizer, with an error that goes like delta t, that is to the 2 times m. M is the order of approximation of the method that you use to approximate the SDE. Particular for m, for the Euler-Maruyama projected method, m is equal 1/2. And so here you have delta t that represent the discretization error. Then you have an error that depends on the number of particles and represent the mean field limit rate that goes like n to the -1. It is independent of the dimension. A dependency of the dimension may appear in the constants, and I will comment about that in a second. And then there is this epsilon that we introduce here that depends on the Laplace principle. I will explain this Laplace principle issue later when the proof come into the game, and I can explain it more clearly. The constant in front of the delta t may depend linearly on the number of particles and the number of dimensions. The constant in front of n depends exponentially on alpha, and if alpha depends on the dimension, there might be a bad dependency of the dimension here. But this would occur mostly for those optimization problems that are originally NP-hard. So problems that do not admit polynomial solutions. So for those problems, we do expect that the constant here would behave badly with the dimension. And here, the constant in front of epsilon depends on C0 and beta. And it does not depend on other things like the dimension or number of particles. So, okay, this is the result that we have. So we can guarantee a certain convergence, at least in expected value, to the global minimizer with this three-level approximation type of error. So how does it work, the proof? Well, the proof is done as follows. First of all, one establish the well-posedness of the multi-particle system of the original SDE that I introduced to you. Then one introduce a monoparticle self-consistent nonlinear SDE. So this is a monoparticle where instead of having the body center computed by the empirical measure of the particles, one use the law of this monoparticle process. And therefore, somehow, this is a sort of, yeah, it's a monoparticle system. Then one proved that the law is solving a partial differential equation of Fokker-Planck type, where somehow everything is defined actually on the sphere. In particular, the differential operators are projected on the tangent plane. This is the corresponding Laplace-Beltrami operator, and this is the typical divergence type of on the operator on the sphere. And so we discovered that the law of this monoparticle system does behave in this following way. The next step is to prove that the empirical measure of the multiparticle system converge to the law of the monoparticle system that solves this equation with a certain rate. And the way we do it is by proving that a certain distance between these two measures does converge in expected value with respect to the this empirical measure, converge with rate n to the -1 as the number of particles goes to infinity. This is the place where somehow on the plane one cannot prove this statement, or at least there is no technique yet to prove it in the case of unbounded objective. And here we take advantage of the compactness of the sphere and the boundedness and the boundedness of the objective function to be really able to prove this rate. Along the line, we will need a little bit more regularity of the solution. So we need that the solution is not only probability distribution, but it is actually an L2 function whose L2 norm can be bounded. And so we will see where this issue come into the game. So we need to have a little bit more regularity, and that's another important step of the proof that would allow us then to show the large time behavior of rho t. So we can show that at a finite time t star, and for alpha large enough, the expected value of the law at time t will be very close to v star, and with an epsilon error that comes into the game. And then there is the concluding step that is nothing else than a sort of triangle-like inequality combined with Jensen type of inequalities. And what you get is basically that the distance between the algorithm iterations on average is not far from the average of the solutions of the SDE system, the expected distance from the empirical measure from the law can be bounded by this rate, and then the expected value of the law is not far from the global minimizer, and by putting together these three levels of approximations, one gets the final result. Okay, this is how the architecture of the proof and how somehow the analysis of these optimization methods would go. Now, let's see how all these steps are realized one by one, especially for PhD students that may not have seen this kind of techniques or problems. The way we approach it is, the fact is, you can try to analyze these methods by try to describe it in intrinsic coordinates of the sphere. But the problem with that is that then you kind of have to analyze everything by using moving frames, moving atlas on the spheres. And this is a very complicated thing to do, especially if you want to then have a global analysis of what is going on. At the same time, you want to have an implementation of the method. And for this reason, we are embedding the sphere in RD, and we try to understand how to analyze the sphere within the somehow coordinate system that we have in RD. And this is what we do. So we first of all look at the stochastic differential equation system as it were a system in RD and not a system on the sphere. In particular, we extend operators that are on the sphere in a very smooth way, especially when they become singular. For instance, some of them would become singular at 0, like v divided by v squared, or the projection onto the tangent plane will become also somehow singular at 0. And so we kind of cut off these functions and we make them smooth everywhere. By doing so, we redefine a system of SDEs in RD where those projections or those terms that would have a sort of blow up in 0, they are smoothed out. And what we prove is that this system is well posed. At the same time, it never leaves the sphere. So whatever happens in 0 is never seen by the system because the system will keep moving on the sphere. This is the way we approach the problem. And in particular, the first thing that you have to prove is that the terms that are appearing here are all Lipschitz and have at most the linear growth. And that's exactly what you can prove by kind of estimating the Lipschitz continuity and the growth. And by using then standard results on pathwise solution of these SDEs based on local Lipschitz continuity and so on, you can prove the existence of a solution. But then the Ito formula applied to the norm squared, so the differential of the norm squared, can allow you to prove that using all the terms, including the third one that I mentioned to you, that was a sort of higher order correction, would allow you to prove that the solution of the system, if there exists, is always having a constant norm. And so if you start from initial condition on the sphere, you will stay on the sphere. So the solution is actually bounded, and therefore it's also a global solution. That's the way you prove that the system of SDEs is well posed and it is moving on the sphere. As we mentioned before, we also introduce a monoparticle dynamics that is self-consistent in the sense that in this computation of the body center, we use the law of of the monoparticle itself, and we want to prove the well-posedness of this equation. The way you do it is by linearizing the problem. So first of all, you substitute the barycenter with an arbitrary field, and then by classical methods, by classical Lipschitz, Cauchy-Lipschitz theory, you can prove that this would have a solution. But then the solution generates a law, and with this law, you generate a new field, and so on and so on. And so you construct a map that maps a certain type of monoparticle system into another monoparticle system, and you try to prove that somehow this map is essentially having a fixed point, and for that you use a classical Leray-Schauder fixed point map, and that's how you prove this kind of existence. Okay, so the uniqueness of the method follows by isometry and Gromwall, and so also this is not too complicated. Okay, now that one has at disposal the monoparticle dynamics, one can test this monoparticle dynamics with respect to a test function phi that is sufficiently smooth. And by using Ito calculus and the expression of the differential of the monoparticle dynamics, one can get this explicit expression. And by taking the expected values on both sides, you have to interpret it as an integral form. By interpret it in the integral form, you take the expectation both sides, you use Fubini-Tonelli, and then basically you can prove that somehow the law of this monoparticle system can be described by an equation that is written here in weak form. This equation is tested with respect to test function on RD. But what we know is that this law is not supported everywhere. It's supported actually on the sphere. And therefore, we can simply test this on test functions that are defined on the sphere, and they can get extended in a normal direction to become smooth functions outside, right? So we can define a new measure mu that is actually purely defined on the sphere by testing it on test functions that are extended outside, and somehow you want that this identity is fulfilled for such test functions. And so if we restrict to such test functions, it turns out that the law that we have here allows you to substitute the differential operators that are appearing here, that are the classical differential operators in RD, to the corresponding projections onto the tangent plane of the sphere. And so you ended up proving that the PDE that we mentioned at the beginning is in fact fulfilled by the law, and therefore it has a solution that is the law of the monoparticle system. And the uniqueness follows from the uniqueness of the process. As I mentioned to you, one of the crucial steps then is to prove that this mean field limit, quantitative mean field limit. Quantitative means that you have a rate of convergence with respect to the number of particles. And the way you do it is by proving that the multi-particle system keeps very close to a multiple monoparticle realizations as soon as the number of particles is sufficiently large. And this happens in expectation. That's the way you prove it. And this would imply that a certain distance of the empirical measure from the law does converge to zero with a certain rate. again in expectation. So how do you prove that this kind of one has this kind of behavior? Well, the way you do it is, first of all, proving that the empirical law associated to the multi-realization of the monoparticle dynamics keeps very close to the body centers, keep very close to the one of its law. And this is proven by a sort of large somehow theorem of large numbers, or sort of large deviation bound, that is possible exclusively because we are on a compact set. So the presence of this exponential with respect to the objective will make it in general quite difficult to have this kind of inequality. But because of the objective is bounded, it's possible to obtain it. And then one compare these two dynamics by comparing the two equations. So one can write the dynamics of V and the dynamics of V bar in an integral form. You take the estimated value, and then you do a bunch of inequalities. You keep into account that the body centers behave like that. And because of this, one can end up with a sort of Grunwald type of inequality problem that you can solve by Grunwald. You can apply the Grunwald inequality to this kind of dynamics, and because of this Cn to the -1 rate, you end up with these estimates. Okay, so now all the steps are there. So we have the well-posedness of the multiparticle system. We have the well-posedness of the monoparticle dynamics. The monoparticle dynamics as a law solving a PDE. We proved the mean field limit of the somehow empirical measure converging to the law. And now we want to discuss what happens to the law in as soon as somehow the time progresses. And here we define two macro quantities: the estimated value of the law, that is the integral of V over the sphere of the law. And the second is the variance. And these are morally expected values on RD and variance on RD. Okay, so this is more or less how they look like. And now I introduce two quantities. The first quantity is the exponential of alpha times the supremum of the maximum of the objective and the minimum, and the difference between the maximum and the minimum. And then a quantity that depends on the variance of the Brownian motion and the dimensionality. Now we introduce the Laplace principle. And the Laplace principle tells that you can approximate the minimum of a certain objective over the support of a measure by taking the limit for alpha going to infinity of the minus 1 over alpha, the logarithm of a certain integral of the measure of an exponential e to the minus alpha, the objective function itself. So this is how come that we defined the famous body center with this particular weight, and this is due to this very nice identity that one can prove by taking the logarithm to the classical well-known fact that L alpha norms converge to the L infinity norm for alpha going to infinity for functions that are sufficiently integrable. So if you want to prove it, you show that you take this function and you take the alpha norm, and the alpha norm of that has to converge to the L infinity norm, and by taking the logarithm of this, you get to this identity. Okay, this is the way you prove the Laplace principle. The other important ingredient is the inverse continuity property that I already introduced you from the beginning. And by combining the two things, what you get is the following inequality. So if in the inverse continuity property, you plug inside, instead of V, the expected value of rho t, okay, then what you get here is E of the expected value of rho t. But now one can substitute to a certain extent to this difference, basically this integral as it appears here. And so by alpha large enough, up to a certain error, epsilon, that depends on how large alpha is, okay, we can obtain here the variance that would allow you to exchange the expected value rho with within somehow this expression, and what you gain is the variance at this point. So by the fact that we combining these two equations or the two ingredients, you get this inequality, and what you can see is that making small the distance of the expected value from the global minimizer is obtained as soon as the variance goes to 0 and alpha has been chosen large enough so that this epsilon is small enough. Okay, so this is the way somehow one can try to prove convergence of the expected value to V star. So it's all about the variance. And so we can do a variance analysis. And so if you use the Fokker-Planck equation that describe the dynamics of rho, one can study the behavior of the variance, and after some massage of the equation and proper estimation, what you get is that the variance will go like a minus lambda times the variance itself, plus some positive constants, the variance. So the idea would be to try to balance the difference between these two guys so that you can gain a negative sign, so that you can show, in a certain sense, the exponential decay of the variance to 0. But then all these other terms that are appearing, the ones between the first big brackets here and the second term over there, this term here, they should also play at your advantage. And what it comes into the game is that, and this is the well preparation of the problem that I mentioned to you as a condition for the mechanism to work, is that if the variance is small enough, the expected value is already quite close to the to 1, so it means that is already quite close to the sphere. The scalar product of the expected value with respect to V alpha is also very close to 1, and V alpha is also very close to 1. So all these terms that are appearing here, they are kind of about a constant. Okay, they are not bothering you too much. One can also prove by using the famous regularity, this L2 regularity of the solution, that also this term that appear here, that has a positive sign, is actually a lambda times a theta, with a theta that is a small number. So it's strictly less than 1. And for that reason, the total number of that you can gain here is negative. And because of that, you can prove the convergence, the exponential convergence of the variance to 0, which means that we can also prove the convergence of the expected value to the global minimizer. Okay, this is the way eventually one conclude. One has to put all together these 3 levels of approximations that I already explained, and that's how somehow this works. Okay. Now, let me show you some examples of applications. One application is the so-called phase retrieval problem. So let's test these algorithms on real-life problems. One of these problem is the so-called phase retrieval problem. And here we have an unknown vector z star that we want to learn by observing the square of the scalar products of this vector against other unknown vectors, plus a possible adversarial noise, so something that is disturbing the measurements. This problem is well known. It's a problem that comes with X-ray crystallography, because if the AI are complex exponentials, what you get here are Fourier coefficients, and what you get is actually what you get here is only the amplitude, and you kind of fail to gain information about the phase. Okay, so you learn a lot about the amplitude, but you don't have the phase, and not having the phase does not allow you to use the Fourier analysis to be able to recompute back Z star. And that's exactly what happens in X-ray crystallography, where, for instance, you take a molecule of DNA, and you try to learn the molecule of DNA by looking at an X-ray projection. And this X-ray projection is actually a sort of diffraction figure that is nothing else a Fourier transform of it, but what you see is only the amplitude. And so when they discovered the shape of the DNA, what they actually did was to solve this phase retrieval problem. So they had to find Z out of only the amplitude information. And how do you do that? Well, what you do, you create this optimization cost, and you try to find the function Z, or the vector Z, that indeed minimize the distance between the observed measurements and the scalar products with these known vectors in absolute value squared. This is a quartic function in very high dimension that you want to minimize. Now, I don't get into the details, but it's possible by some tricks to show that this problem can be constrained on the sphere. So you can reduce the problem to a problem that is fully constrained on the sphere. And so if we compare the consensus-based optimization with many other algorithms that have been designed to solve this problem, so state-of-the-art algorithms, including algorithms that make use of gradient information, which means that they use higher order information, it turns out that if you compare the consensus-based optimization with these algorithms, it works perfectly well for this problem. So you don't need an ad hoc method in a certain sense. You take the consensus-based optimization and you make it working for this problem. The funny thing is that we don't need any gradient information, and it works pretty well. And somehow this is an experiment in dimension 32 that, however, it's already a significant dimension. If there were a curse of dimensionality, means an exponential dependency on the dimension, this would be already visible. So the fact that we are able to solve the problem means that somehow the problem is not NP hard and the method is not affected by the curse of dimensionality. Here there is another problem that is called the robust linear regression, or if you want the so-called robust subspace detection, that is about fitting a cloud of points in high dimension. And we fit it with, first of all, with a one-dimensional space. We want to find the best one-dimensional space that fit a cloud of points. This is a classical regression problem if you consider minimizing the square distance of the points from the subspace. So for p equal to 2, say if the points are xi, we want to find that vector v that represents the direction of the one-dimensional space in such a way that the distance of the points from this subspace is minimized. And with p equal to 2, this is the classical linear regression that is solved by singular value decomposition of the matrix that is built with the points of the cloud. But for p less than 2, and in particular p less than 1, this problem becomes essentially very, very difficult, and with a lot of many local minimizers, and there will be no gradient method that would converge to the global minimizer. Why do we need p less than 2? Because if a point is very, very far from the linear subspace, so in a certain sense it's an outlier, because fitting the subspace means that it should be close, every point should be close to it, right? But if there is an outlier, so a guy that is very, very far from the linear subspace, and I weight the distance quadratically, means that this guy within this sum counts a lot. And so whenever you have outliers in linear regression, the linear regression won't work anymore. But if you have a non-convex function like 1 over 1/2, then all of a sudden you are counting the guys that are very close to the linear subspace more than the guys that are very far away, because the guys are very far away, you count them with the power 1/2. Okay, so it's a kind of way to make it more robust. So let's try to use it on a subspace of use it to interpolate, in a certain sense, or finding the best possible fitting face to a group of faces by introducing also outliers and see what happens. So you can see on the left, in the case where no outliers are present in the point cloud, and we compute the solution by the singular value decomposition, you get this face. And you can use the CBO method also to solve that problem. And what you can see is that the solution is the same. By the way, it's really funny, because if you take a Facebook and then you try to compute the best fitting phase, or the eigenface of the system, what you get is it's kind of Mark Zuckerberg, okay, right? It's kind of funny, but nevertheless, okay. Now let's assume that there are some outliers, and if you use SVD, you see that the outliers are distorting completely the situation because they pull away somehow. But if you use the optimization, this optimization for p less than 1, and you use, say, a CBO method, what you get is still relatively clean image and more robust linear regression. In case you have even more outliers, the distortion is even stronger, but still somehow using CBO method for, say, p equal to 1 or p equal to 1/2 would allow you to have still a reasonable solution. Okay, with this, I think that I explored pretty much all from the concept, the analysis, the modeling, the analysis, the numerical analysis, and its applications in machine learning. And with that, I would like to thank you, and I promise to you to give you the literature, and that's more or less the fundamental papers now. There are more papers that we produced, papers that show that you can do a an analysis that is not based on variance analysis, and this would allow you to avoid this well preparation of the initial conditions and also the smoothness of the objective. And we have results on non-isotropic noise that would allow to push even to higher dimension the possibility of using these methods. And there are many more papers that come in the business, in particular on the connection between CBO methods and particle swarm optimization. So it's a field that is kind of expanding very quickly because it has a lot of applications. It's pretty beautiful, and also the analysis is pretty challenging. And so that's all I wanted to say.